Go ahead. You're
the
one.
Gaussian integral, she talks about the integral of any odd function between -infinity and infinity being equal to 0. So for one of the homework problems, there is an integral like that where we have the function f e to the negative alpha x squared. So we can just write that it is equal to 0.
Yes, that's right. That's right. That's showing your aptitude with calculus.
Because in the next homework, it tells us to find the answer to the integral and then justify it using the symmetry of the equation. But it seems like we should just be able to go straight to the symmetry of the equation to find the answer.
Yeah, unless specifically told like otherwise, yeah. Okay, picking up where we left off last class period, we had checked this function here to see if it was linear. So we'll go on to the next one now. So we're going to take the second one that has the square. And I have to put in another page. So checking operator 2 acting on f of x gives us f of x quantity squared. I wrote it a little bit differently here. I think that's different. Nope, it's exactly the same. So there's two tests. Test 1 is to check to see if I have a complex function, if it's going to work as a complex function, function 1 plus function 2. So operator 2 on f of x plus g of x. See if that is equal to operator 2 on f of x plus operator 2 on g of x. So since we've had, I'm going to sit down. It's already been a long day. It was those calculus students. So what will I get when this operator 2 acts on the fx plus gx?
F of x plus g of x in brackets squared, all of that squared.
Okay, I will get, should have stayed with blue, huh? Okay, so that's what we get for the left side. Notice I left these in the order they were originally. When we get to quantum physics, it's generally safer to keep things in order.
Is that because things can be complex?
I think it's only really important when you have an operator acting on a function. In fact, I'm pretty sure it is. But sometimes you can have an operator acting on an operator, and it's just then going to be safer to do that. I mean, we know logically those two are the same thing, right? No matter what the function is, function A times function B is the same thing, right? As function B times function A. So that's what I get for the left-hand side. What do I get for the right-hand side? So those are definitely not equal. You have these two terms here on the left side that you don't have on the right side. So it fails test 1. But then I'm going to go ahead and test the second one as well. not Q, O2 And so when we look at this on the left side, we're going to have a f of x squared. On the right side, we have a f of x squared. When I said it, it sounded the same, but they're not the same because this has a squared, and this one just has a. So it fails the second test as well. Finally, the third one. O3 acting on f of x equals f of, what is it, x squared plus 3, something like that. 3x squared plus 1. It doesn't really matter as far as the test goes, but we want to actually test the one that's given. And so then test 1, O3 on so there's our test. So we substitute. And so everywhere we had an x, it becomes 3x squared plus 1. So I'm going to have, replace the x with 3x squared plus 1 everywhere it appears. And lo and behold, that one passes. Now that's test 1. You have to run test 2 if it passes because it's only failures that tell you anything definitive. So test 2, O3 AF of X equals question mark O3 or AO3 F of X. And doesn't affect the A. And notice by this point, I'm just going really fast because all we're doing is applying the operator, and these are simple operators. And so both of those are true, so it passes. So I know I told you at the end of class last period that it was going to pass, but you can see how it passes. So any question on how to test operators to see if they are linear?
Can I ask about a couple from the homework?
Yes, absolutely. Let me add another page here. Yep, I am much more concerned with you understanding than I am with you not having any help or doing all of the homework without help. You know what I mean?
Yeah. I
want you to know. So go ahead.
Okay, so for C, we've got O3 psi of x is equal to lambda psi star x.
Okay.
Yeah, and I'm pretty sure test 2 passed, but I'm not sure.
Okay, so test 1. So I'm going to O3 acting on, and I'm going to use F instead of psi, F and G, just like we did. So there's our start. There's our test we're going to check. So now I go through and I'm going to take this entire thing and take lambda times the star of this, right? And so a complex conjugate is just going to come into each one.
Okay, so it does distribute.
So there's the left-hand side. And on this side, it's going to be and so are those equal to each other?
Yeah.
Yes. So passes test 1. Now, I don't remember what you said about test 1 versus test 2,
Let's
but
just do test 2 as well.
okay, good. Because I can't stop halfway.
Yeah.
So we have O3 acting on A f of x equals question mark AO3 acting on f of x. So here I'm going to have which is equal to that.
Okay, so A can be complex.
A could be, it didn't say that A had to be real. That's
Okay.
correct. So since A can be complex, then fails. If A had to be real, which it doesn't, right? But if it had to be real, then it would pass.
And then for F, there was just, it looks like kind of some odd notation that was being used for the operator.
Okay, so what was the operator for F?
O6 psi of x is equal to the integral from negative infinity to x of dx prime, dx prime psi of x prime times x prime.
Okay, now the reason it has x primes in there is because you can't have your limit and your variable of integration the same thing.
Okay.
But we're going to end up with a function of x after we do this because of the limits. So now for testing, it wasn't OF, it was O6, wasn't it? I know it makes such a world of difference, but and so when we do this, we have properties of integrals now. Integrals, you can separate them. And so that's and then we're checking to see if that equals, well, exactly that. And so was that a pass or a fail? And then we go to test 2. And test 2 it's trivial because that's one of our rules of integrals, that a constant can move through the integral. But just, we're doing the work. And so the fact that A is a constant means that you can bring the A out and it passes.
So is there a particular reason why you wrote the dx prime in front of the f of x and the x prime?
I heard you say it that way. That's the only reason.
Right, but like in the problem, is there a specific reason why it's written that way? I just don't see it typically.
Different authors, different textbooks have different preferences. And I copied these from a textbook, just not our textbook.
Would you generally write it the other way?
I usually would, yes, because that's the way I'm more comfortable with it.
Yeah.
I like to encapsulate between the integral sign and the dx. There are some times when I do things like this when I have multiple integrals, and then I'll put the d with the integral sign so I keep track of which limits go with which variable.
Yeah.
But in this case, there's no point in doing that because it's only one variable.
Okay. Thank you.
Okay. Dad, do you have any homework questions you want to ask?
Well, I just found out that I did this last one wrong. It's just equal to 0. Or expectation value just equals 0 because it's an odd.
Oh.
So, do you want us to evaluate all the way down and then take the integral and show?
Well, you should always do it the most efficient way that you know how. So if you can say, oh, this is a symmetric integral, then it's 2 times integral from 0 to infinity. If it's an anti-symmetric integral, then you just say this is 0 based on an anti-symmetric odd function, right? Even function is symmetric. Okay, now I'm going to go through the uncertainty principle stuff, and we'll actually finish it, which means we finished all the stuff for the test next Wednesday. And then I will go through doing some problems to give us some actual practical experience. You've got some homework problems. We'll do other problems. So the uncertainty principle, we will very carefully describe the uncertainty principle later. We will derive it the whole 9 yards. But for now, we're looking at it in a very handshaking way, just so you know what the uncertainty principle is. So I know Aaron has at least heard of the uncertainty principle. So I'm going to turn to Chad. What do you know about the uncertainty principle? Nothing. Okay, that's fair. I mean, after all, you haven't been through second semester of physics, so you're not supposed to have had any quantum mechanics. Anything you knew would have been picked up from elsewhere. So the uncertainty principle is something that Heisenberg originally determined. And it's one of those things that, remember, we started with the orthodox view, the realistic view, and the agnostic view of quantum mechanics. And the realist view has a real problem with the uncertainty principle, because what it says is the better we know something, the less we know something else. First thing about the uncertainty principle, it is not exclusive to position and momentum, or position and speed, as you might think about it. There are different uncertainty relations, and we will learn how to determine if 2 variables have an uncertainty relation or not. Now, how is this in any way important? Remember last class period I was talking about our momentum operator doesn't share the same function space as our position operator, right? So our position operator operating on psi as a function of x and t gives us position times psi as a function of x and t. No problem. But the momentum operator doesn't give us back that function. If we have that situation, then we're going to have an uncertainty relation. We can't know both of them exactly at the same time. So where does it come from? This here is the general physics hand-waving explanation. If we have a matter wave, we have a particle, and I'm just going to, if we have a wave and we know exactly the wavelength, then the wave is going like this, and it continues like this forever. If we know exactly the wavelength, it can never end. And so if this is our wave function, then if I'm going to calculate my probability density, I have to square this. And if I square this, I'm going to get okay, so my artistry kind of fails because, of course, my wavelength did appear to change over space. But keep in mind, that's just my artistry. And now if I ask you, where is the particle associated with this wave, your answer is going to be, well, it has an equally high probability of being at each of these peaks with diminishing probabilities everywhere else and zero probability of being found at these minima.
So it has the highest in general, like the particle is most likely to be found at the point with the
when you
highest peak,
the highest displacement when you square it. But there's an infinite number of those, and if I ask you where is it, you can't even say, oh, it's more likely in this region than this region. You can only say, well, it's more likely at these points than anywhere else. So your uncertainty on its position is infinite. You have no idea where it is if you know exactly what its wavelength is. And using de Broglie's, that's how you actually pronounce this. It's not de Broglie, it's de Broglie. I made a point of that last year thinking my students were going to be shocked. No, they're like, no, Dr. Lang always says de Broglie. Okay then, because I had never had a teacher who said de Broglie. My teachers had always said de Broglie. I mean, we're Americans. So using the de Broglie equation, momentum is just Planck's constant divided by wavelength. So if you know exactly the wavelength, you have no uncertainty in that momentum. And so if you know exactly the wavelength, you know exactly what the momentum is, but you have no idea where the particle is. That's the hand-waving explanation. And if you make a wave packet, so my next slide here has a wave packet, make a wave packet with some, now this here has K. K is called the wave number, and the wave number is defined as 2 pi divided by the wavelength. So when you look at that, this here is something that has to do with the wavelength. And so if you have a packet with, well, here's the physical packet. Your wave is somewhere, okay, it approaches zero at plus or minus infinity. We basically say, okay, at one standard deviation on either side, it's probably within there. So we have an uncertainty. I mean, you can't have a really good probability that it's in this range. But in order to make this packet, you have to introduce different wavelengths. You can't make a packet with one wavelength, right? You have this outer shape that needs to be described with a function of the wavelengths. And so it turns out that this is what the wavelength distribution is going to, well, the wave number distribution is going to look like for that wave packet. And so once again, you can say, here's my uncertainty about the average for the wave number. Here's my uncertainty for position here. And now I have a relationship that I can make between the uncertainty in the wave number and the uncertainty in the position. And since momentum is h bar times the wave number, then the uncertainty in momentum is equal to h bar times the uncertainty in the wave number. I know it's really unfortunate that K, which always stands for constant, now is a wave number, which is not constant. And so we can make a relationship between those. And that's what Gauss did. Gauss, and his name is, by the way, pronounced Gauss. Some people say Gauss. First time I had students say that, I was like, I don't know what you're talking about. He was talking about a gauze gun. I thought he was talking about a gun that shoots gauze. That guy's now a doctor in physics, by the way. He went to medical school and then he decided to go study physics instead.
Did he make a gauze gun? I feel like if he didn't, he failed.
Yeah, I mean, in medical school, you have plenty of gauze. So. It's people in graphics, they often call it a Gaussian blur because, well, we'll go on. So what Gauss did is he used a Gaussian distribution and showed that mathematically the Gaussian distribution gives you the smallest possible product between the uncertainty in momentum and the uncertainty in position. And that gave him his value of h bar over 2. Now, let me remind you, we've used h bar a lot. What is h bar?
H over 2 pi.
Yes. Just wanted to make sure we remember that rather than like forgetting that it has a tie-in to something we're more comfortable with.
Do we need to memorize the number?
No.
Yeah, do we need to memorize equations?
I was going over my review lecture, which I will probably give it tomorrow so that you have a whole week after the review lecture to think about it for the test. And then just go over more problems and stuff next Tuesday. But it has in there exactly what equations you're going to have and what you won't have. And so you will have the operators. I noticed the wording I used last year said you would have but wouldn't have the operators, kind of like quantum physics. But you'll have the operators. You don't have to have the operators memorized. But you'll have to know certain things like the normalization. I think you have to know what the normalization condition is. And so I'll specify that in my review lecture because I've got it written down. I don't remember on the top of my head. Okay. So this is the result that Heisenberg found. I said Gauss showed. Heisenberg showed using a Gaussian. I said Gauss a bunch of times there by mistake. It's Heisenberg that showed the uncertainty relation using a Gaussian distribution. He showed that the Gaussian distribution gives you the smallest possible. And so he comes up with this that we take as a law. It's a law that tells us about the probabilistic nature and the fact that you can't know these two things at once. And so that leads you to the silly jokes. Heisenberg and Schrodinger, and I forgot the third person, are driving in a car and they get pulled over and the officer says, "Do you know how fast you're driving, sir?" And Heisenberg says, "No, officer." The officer says, "You were doing 73 miles an hour." And Heisenberg says, "Great, now I'm completely lost." Because, of course, if you know your speed exactly, then you have no idea what your position is. And then the officer, based on his response, thinks these guys might be on drugs. And so he says, "Can I search your trunk?" And so he complies, opens the trunk, he comes back and says, "Did you know there's a dead cat in your trunk?" And then Schrodinger blows up. Anyway, now I do. Anyway, we have those kind of jokes because you know what physicists are? They are funny, funny people. Good senses of humor all around. Speaking of which, time to do some problems. So I put in a bunch of pages. Would like to do problem 1.9 on page 20. It A gives us some practice with those stupid Gaussian integrals. And B is not one that I made you do, right? Although it's very similar. So that's better to have the practice problem harder and the homework easier, right? And remember, for any of these problems, if you're preparing for the test and you look at a problem, I have a link on the Moodle website to another website where a guy has done every single problem in the entire book with pretty good explanations for each one.
Oh, so it's not the author who did the?
No.
Wow, because that's like very thorough.
Yeah, it's very thorough, yes. I appreciate that, and that's why you don't have any homework problems from the textbook, because it's very thorough. So we have, I haven't looked at the new textbook actually, but I'm guessing that he might have switched up the homework problems just a bit, because it's hard for a teacher if you have all of the homework problems are easily available to everybody. Okay, that's what they give us for the wave function. I would be more prone to write it like this. Just because I like to get the is it a -7? That's
I think the A is in front of the whole thing.
Oh, you're right. You're right. It is. Okay, I'm going to make that in red here. And so that's minus IAT here. So I would write it like this just to get the imaginary part separate from the real part. It just makes me feel better. Both of them are perfectly acceptable. There's no error either way. And unless, of course, I made an error writing. But thanks to Aaron, I have not. Now, this problem tells us specifically, and this is important, A and A are real. So that means when I do the complex conjugate, it doesn't affect those. And then we have part A with no pretense. Find capital A. So now you as the student have to say, what's the method by which I can find what capital A is? You normalize it. So find capital A is code for normalize it. Because A, after all, we call it the normalization constant. So then I have to do my equation or my calculation. So what is the calculation for normalization?
1 is equal to the integral from negative infinity to infinity. I'm just going to do psi star xt times psi xt dx.
I wouldn't even have said the xt. I would just say psi star psi dx. And so I'll write psi star first. Remember, no star for the A because it's real. So there in green is the first one, the psi star. Notice I changed the sign for the second term because of the I. And then that's perfect. Trying to do some color coding. So my integration stuff is in red, my psi star is in green, and my psi is in blue. So now simplifying, that's going to be a squared, a is a constant, integral from minus infinity to infinity. And notice the e to the iat times e to the minus at is e to the 0, which is just 1, so we don't write it down.
Can you say that again?
Yes. Okay, I will write it down then. So there I added the exponents of the real ones. And added the exponents for the imaginary ones. And the imaginary ones have opposite signs, so they add up to 0. So that's e to the 0. And e to the 0 equals 1. So that whole term is just 1. So what I said was I'm not going to write it, but because you questioned, I figured it's going to be safer to write it out so you know exactly why it's disappeared. And these two here, they just add up to double. So it's a squared integral from minus infinity to plus infinity e to the minus 2a m x squared over h bar dx. And what do we do from this point? Okay, we realize it's an even function. To a squared integral from 0 to infinity. So I just cut it in half. E to the minus 2a m x squared over h bar dx. Then what do I do? Yep. Integral from 0 to infinity of e to the minus bx squared dx is equal to 1/2 square root of pi over b. Right, that comes from the integral table. So I recognize that b is equal to 2am over h bar. So I end up with 1 is equal to don't forget the 2a squared that's out front times 1/2 square root pi h bar over 2am. The 2's cancel. Solve this for a. A squared is equal to square root of 2am over pi h bar. And so a, what's the value for a?
Just 2a over pi h bar. Oh, square root instead of the 1/4.
Fourth row, yeah, right. 2am over pi h bar to the 1/4 power. You're probably seeing why in that homework problem you had, there was a normalization factor of what was it? 4th root of alpha over pi, was it? Something like that?
Yeah.
Right, because that's how you normalized it. They gave it to us in the previous one. Here we had to calculate. So there's our first step, part A. We have found A. Any questions at this point?
If you have us do that, would you like us to write out the whole case sheet?
No, if it says find A, I just,
Okay.
yeah. And there's no reason to do extra. I mean, obviously I wouldn't write, oh, you lost a point because you wrote it out, but okay, part B. Part B says, for what potential energy function does psi satisfy the Schrodinger equation? So we have to remember the Schrodinger equation, which is I h bar partial derivative with respect to time of psi is equal to minus h bar squared over 2m second partial of psi with respect to x squared plus v psi. That is correct, right? Because, you know. Yes. It's, you actually have to combine the first and third equations in the front cover to get the Schrodinger equation, but that is it. In case you've looked at the front cover and you're wondering, wait a minute, the front cover has for the Schrodinger equation, instead of d, well, I'm not going to erase it. Instead of d second psi, it has that. This is a three-dimensional second derivative. So the equation shown in the front cover is using 3 dimensions of space, whereas what we've been working on so far has been simply 1 dimension of space. So nothing crazy to get concerned about there as long as you know what that is. And if you're uncomfortable with that, fine, we'll deal with it later. So all we have to do now is put in our Schrodinger equation. You know what I'm going to do? I'm going to continue to use A, right? Because A is much shorter to write than the stuff we just found. So I'm going to have I h bar d dt of A e to the minus A right, that was the Schrodinger equation, correct? I could turn my book back and just read it. Yeah. Oops, I got to reposition it. Oh, shoot. So that's what we're going to use to solve for V. Well, our lives will be simpler if we do our derivatives separately. So the derivative with respect to time of psi is equal to, and all I have to do is bring down minus IA, oops, lowercase a. And then all the rest of psi is the same. So I wrote out the long way here, but then I did the derivative mostly in my head. Right, the only thing that had time in it was e to the iat, so that's the only part that I had to worry about taking the derivative of. The derivative with respect to time of e to the minus iat is going to bring down a minus ia and then be the same. Similarly, doing the position derivative, I can ignore the e to the iat, but it's much more complicated. So d second dx squared of psi is equal to d dx of d psi dx. I'm going to start with that. What's the derivative of psi with respect to x?
We're going to bring down a negative 2am over h bar.
Minus 2amx over h bar. Right, you have to bring down the derivative of the exponent. And since the exponent has an x squared, I had to bring down minus 2amx over h bar. Well, that's a little more complicated for the second derivative because I'm going to have to use the product rule for the second derivative. So my second derivative is equal to derivative of the first minus 2am over h bar times the second plus the first minus 2amx over h bar times the derivative of psi, which is minus 2amx over h bar psi. So there I have my second derivative with respect to x of psi. A little more complicated, right? So now we're just going to see what v has to be. So putting it all together, I have I h bar times this. Zoom out appropriate and we can see everything on the page. So there in red is the derivative with respect to, second derivative with respect to position. I'll make the first derivative with respect to time blue. Minus IA psi. And then finally, plus V psi. Notice I wrote out all the psi stuff, but I didn't actually use that. I did my derivative separately, and now I have three functions, all with psi in them. And so I will just bring everything together on one side of the equation. So I h bar times minus IA. I times I is minus 1. So negative and minus 1 is positive. And I'm going to have A h bar times psi is this term. I'm going to bring the other two terms across the equal sign. So the next one's going to be a plus sign h bar. Now, h bar squared, I'll write it all out. So there in red is the derivative, second derivative with respect to x term. And then I realize I screwed up my color coordination. And then in green will be the last one. So either psi has to be 0 or everything inside parentheses has to be 0, which allows us to quickly solve for v. Notice one of those cancel, those cancel, one of those cancel. That's a minus AH bar. And then my next term, the h squareds cancel. 1m cancels. That becomes a 2. And so that's what the potential energy function is going to have to be to get this Schrodinger equation, or to get this solution from the Schrodinger equation. We're going to do this problem starting from the other side. We're going to start with the potential energy function because that is the potential energy function for a simple harmonic oscillator. And so we're going to work from there to finding the solution later on. Any questions about this? Notice it's taking me, now I'm writing kind of big, but it's taking me a page for part A and a page for part B. These aren't little trivial steps. Any questions though? Am I out of time? I'm out of time. Wow. We really crushed it this class period. Just forced it through. Well, I will finish. I will do parts C and D at the beginning of next class period. Then I'll do some review. Hopefully then we can do more problems next Tuesday and then have tests on Wednesday. I'm sorry, I don't look at the time, just having a good time.